Hello, everyone. This is Paul Nauman joining you this afternoon. Thanks for joining this presentation. Today, we're going to take a look through the Java Virtual Machine, piece of software that we use a lot when we run Java stuff. And it turns out to be a pretty complicated and impressive piece of software. But it does help to understand a little bit about how it works. So in this presentation, we'll take a tour through that, look at how it's specified to run and how it's actually been implemented. And then we're going to focus specifically on one piece of the virtual machine, which is garbage collection. So let me move on here. Sorry. There we go. Okay. So here's what we're going to try and cover in half an hour. I hope I don't go too long here. Like I said, first thing we're going to do is look at the virtual machine model, which is the specification for how the Java virtual machine is supposed to work. Then we'll go under the covers and look at some of the tricks and techniques that have been used to make it performant. And then, as I said a moment ago, we'll take a specific look at garbage collection. Okay, so just a brief bit of introduction for me. I'm currently an application engineer at Azul Systems. Been here about 5 years. Was previously at Oracle, where I was a JVM engineer and worked on fixing bugs on both JRuck and Hotspot. It's where I got my knowledge of JVM internals. And have done a little bit of presenting a couple times at Java 1, what used to be Java 1, and have also presented at a bunch of different jugs in and around the Midwest or the central third of the country. So, so this is, oddly enough, something I enjoy doing. Okay, so let's take a look at the Java Virtual Machine. And before we do that, let's just take a quick look at some terminology. So we often talk about the JVM and the JDK, and we used to, at least before JDK 9, we used to talk about something called the JRE. So the JVM is the execution engine, and by itself, it really isn't capable of doing very much. Doesn't have any of the classes that we expect and that we program to for the language API. But it is the important piece of software, and so what we're going to focus on today. The class library is all of those APIs that we use in our programs, and the two of them together form the Java runtime environment, and those are the minimum that are needed to run a Java program that's written to the Java SE specification. A JDK includes the JRE. But also includes a set of tools. So those are the things that you expect to find in the bin directory: the Java C, the Java compiler, JDB, the Java debugger, the jar file that puts together archives and takes them apart, and a couple other tools that are also in there as well. So so that when we say JVM, JRE, and JDK, that's what we're talking about. How does this sort of fit together? Well, the Java application and the Java class library are both written in Java. So I denote that, at least for the purposes of this slide, as Java space. Those are Java modules that have been compiled onto class files, and so they exist in the Java space. The JVM is a native program that runs on your local operating system, or the system, the server operating system, or whatever, computer operating system, and it relies on a set of libraries. Some of them standard, some of them are made specifically for the JVM. But both of those are in native space, meaning that they are encoded in the native instructions for the particular platform that we're running on. So how does this work? Well, we start out on the left with source files. Those can be those, at least for the purposes of today's discussion, we'll say they're Java. But as we know, there are multiple languages that actually run on the JVM, so they could be other languages. Those get compiled down, and they get compiled into things called class files, which are files that hold all of the information that's necessary for the JVM to run that particular class file. And the class file is the basic unit of execution for the JVM. It's what the JVM reads in. It's what the JVM expects to see, and that's how it gets all of its instructions. So we'll dive down into Java compilation. So this is the first phase of compilation. This is where our Java source file, which is a text file, human readable text file, which contains all the components that you see over there on the left, our class or interface definition. If there's any superclasses or super interfaces, those are listed. Any fields that we define in that class, methods that we define, any references that we have to other classes or other fields or methods in other classes, those are actually encoded in there, and any constants. These last two, the references to other classes or methods and fields in other classes, and these constants are put together in a part of the class file which is called the constant pool. And it turns out that this constant pool is an important sort of central piece of information for the class file and for the JVM. When the JVM reads in a class file, over there on the left, you see the same information is included in the class file, and as you might expect, it simply gets parsed out. So the class file is a binary sort of byte array construct, and when we read it into the JVM, we pull it into an area of the JVM that you may have heard of. We call it metadata. So this is the information about a class, and it's encoded in classes and structures that make it convenient for the JVM to access it and modify it while it's executing. So that is what you might expect. Did I miss something? No. Okay. All right. So so when a JVM is executing and a reference is made to a class or method or field that's in a class that has not yet been loaded, then the JVM actually has to go and go ahead and load it. And it actually does so in a series of phases. And they're listed here. So the first thing you do is actually read it in, and you do that parsing operation that I just showed on the previous slide. The second thing that we need to do is go through a verification phase. And basically, this is a phase where the JVM will go through and it will make sure that the class file is valid, that the bytecodes don't have stack overflows or underflows, that the references all make sense, that the class names are all valid, and things like that. So it's just basically verifying that what the JVM has read in makes sense and isn't going to cause problems later on. The next phase is linking, where we actually take a look at the class and take a look at its external references and see if we can actually link them up to classes, methods, and fields that have already been loaded. And if we have, then we can make a direct linkage rather than the symbolic linkage, which is contained in the class file. So that obviously speeds up execution and speeds up access. And then finally, when the first reference is made to either a class or to one of its members, then we go through an initialization phase where we actually run the static initializers, which are pieces of code that are included in the class. And these are like static methods that run and set up the initial state of the class. And that has to be done before any field or method is actually accessed, before a field is accessed or a method is executed. And it has to be done atomically, meaning if there are several threads that happen to be loading the same class at the same time, the static initializer will be run only once, not multiple times. So, so what does this look like then when we're actually running a Java method? Because Java is all about methods, right? The method is the unit of execution, and so we want to make sure that we know how that works. So here's a diagram that shows how a Java thread is broken down. A thread is basically an ordered list of Java frames, and each frame contains the information that's shown there in the blowout. First is some sort of indication of what the current method is that we're executing, and obviously you need that to be able to get information from that method. Also, the class that contains that method is needed as well, and because we need to be able to get information out of that class. And then finally, this is analogous to sort of an instruction pointer or a program counter in a traditional hardware architecture. We need to know where we are in that method. The method, after all, is just a sequence of byte codes, so we need to keep track of where we are in that. In addition, there are two places where values get pushed on and popped off. The first is the operand stack. So the Java Virtual Machine for each method defines a stack architecture where, in order, for example, to perform an operation on two operands, you actually have to push them on the stack first, then invoke the operand, and then the result will be on the stack when you're done. So it's a slightly different model than we're used to. Maybe if you've worked at a hardware level where you do everything with registers and so on. There have been stack machines in the past, but this is sort of the simplest way. Now again, this is the model of how the JVM is supposed to work, how execution is supposed to proceed. You don't actually have to implement a stack, and we'll see how some of this is done later on. In addition, there are local variables. So those are the local variables that you define for your method. And so there's an array of those, and there's also, and contained in that same array are the parameters that are passed to this method invocation when it's started up. So those are all contained in the same array, same logical array. Again, the JVM can implement this however it wants to, and we'll see an example of how this is done in the next section. So this list of frames, so as methods are invoked, they get pushed onto this list of frames on the thread, and as they complete, as they return, then their frames are popped off, and we resume execution at the previous frame, at the calling frame. So I hope that makes sense. Okay, so I'm going to run through just a few quick examples of how a bytecode works, so you can kind of get a sense for how these things fit together. One of the bytecodes that is in the JVM instruction set is something called new, and that's analogous. In fact, it implements the new operator in the Java language. So when we're creating an instance of a class, we use the new bytecode or an array. And so this is how it's actually encoded in the method. The new bytecode is first, and it's followed immediately by a 2-byte index into the constant pool, which we actually go through a couple of internal references, and you end up at a string which represents the name of the class that we're going to instantiate. And so then the JVM is left with that class name and to try to figure out exactly how it's going to find that class if it's already loaded it, or load it if it has not. So here's a couple of bytecodes that we use frequently. So these are the bytecodes that allow us to get fields out of other objects. or get static fields out of classes. And so again, here on the left is this kind of shows how this is laid out. One of these bytecodes is in the sequence of bytecodes that we're executing. It's immediately followed by another 16-bit index into the constant pool, and that resolves into 3 strings this time: the name of the class that's defined that field, the name of the field, and then the field descriptor, which is a very terse way of describing exactly what type that field is, whether that's a field that contains a pointer to an object or contains a primitive like an integer or a long or a float. So all that's there. So what the JVM then can do with these 3 strings is, again, look through its metadata, find the class that's being referred to, and get the information about the field. And so then we have enough information, if it's, for example, if it's an instance variable in the case of get field and put field, then you actually know where in the object to look for that field. If it's static, then there's information in there about where that static information is being stored. Invocation. So there's actually a 5th kind of invocation, which is not listed here, invoke dynamic, which is far more complicated, and I'm not going to try to get into it in this presentation. But this is how it works. It's very, very similar. Again, we run into one of these bytecodes in the stream of bytecodes as we're executing. It's followed again by a 16-bit index into the constant pool. And after we do the resolution through the constant pool, we end up with 3 strings: the name of the class that contains the method that we're trying to invoke, and the name of the method and the descriptor. And then all of those have to be used by the JVM to find that method, again, loading the class if necessary, and then finding the information about that method, most notably where its bytecodes are, or whether it's been compiled even further into native instruction and internal information like that. So that's the model. Again, the JVM is going to do things that speeds us up considerably, including linking things, so we don't have to go rummaging through the constant pool and doing indirections and comparing strings every time we're invoking a method. But this is the model of how the JVM has to execute. One last thing to mention, and that is the heap. The heap is an area of storage that I suspect everybody knows contains all the class instances and all Java arrays that have been created by the running program. Heap is created at the JVM startup. It's shared among all Java threads, and may be expanded or contracted as needed. There are some JVMs that actually do allow the heap to expand to a point. I don't know of any JVMs that actually contract the heap as memory becomes unused. But important here, and important for what we're going to discuss later on, when objects become unused, there must be some mechanism that automatically reclaims that storage and allows the application to use it again. So, okay, so how does all this stuff work? How does it fit together in a way that executes at a reasonable speed, and we don't have a whole lot of string compares and so on? First thing, once again, we'll start out with some terminology. There's basically 3 different subsystems in the JVM. If you talk to JVM engineers, they'll generally refer to one of these 3. So memory managers is the logical subsystem that manages allocation and reclamation of memory, including garbage collection. Compilers is different than the Java compiler. This is a JIT compiler, which is contained in the JVM, which converts method bytecodes into native instructions at runtime. And in doing so, it can actually take measurements, or profile is the word that we use, can actually profile the program as it's running and figure out which optimizations are going to be the most profitable. So here's some examples of some of the optimizations that the compiler may choose to do. Inlining, where a calling method and a called method get squashed together into one larger method. Boxing and unboxing of variables, optimizing loops, and so on. A lot of this is very sort of traditional compiler technology, but in this case, it's actually done at runtime, and it's done with the guidance of profile information that's been gathered already. And then finally, the last subsystem in the JVM is what's called the runtime, and that basically is everything else. The interpreter, the class loader, the verifier we talked about a moment ago, thread scheduler, and so on. So breaking this down a little bit further from the model that we had earlier, so the Java application and Java class library, once again, are in, quote, Java space. They're expressed in Java. The JVM is a native program which, with the assistance of several libraries, runs on the hardware with the assistance of the operating system. Those three components, the JVM, the libraries, and the operating system, are all in native space, if you will, in that they're expressed in the native instructions of the platform on which we're running. And then, of course, there's the hardware which runs this whole thing. So breaking this down one step further, again, the application and class library in Java space, but the JVM is actually broken into a number of components. The Java executable that we run to start our program is actually referred to as a launcher. It's actually a very small program. Now, all it does is attach a native library, libjvm.so on Linux-like systems, and attach that library, and then start the program, start the Java program. So the Java executable itself is quite small. Most of the JVM implementation is actually in that library. The virtue of that, of course, is that the library can be attached to other programs, other native programs, and so you could actually get Java functionality tacked onto, if you wanted to, tacked onto a native program. The Java class library, in many cases, actually has to rely on some native instructions to do things like opening files, for example, and I/O. And so those libraries get attached at that time as well. So that's kind of the breakdown of how those components fit together. Inside the JVM, most JVMs these days are written in C++, but inside Hotspot, for example, there's a hierarchy that represents the kinds of classes that the JVM has to manage. And so here's the C++ class hierarchy that represents the classes that the JVM is working with. The first and most obvious is the loaded class, which is a class that represents code that somebody has written, has been compiled into a class file, and then gets loaded at runtime. There's two other kinds of classes, a reference array class and a primitive array class, which are simply arrays of either references to other objects or references to primitives like integers or bytes or floats. And so those are different classes as well. So important here is that these are C++ classes, and the classes that are created by the JVM at runtime are actually instances. They're C++ objects that are instances of these C++ classes. So Java classes are instances of C++ classes. It can get quite confusing if you don't keep track of it. So let's see. So how does some of this stuff fit together? Well, let's take an example here where we have a class A, which contains an integer and defines two methods, method 1 and method 2. And then class B is an extension, a subclass of class A, which defines two more integers in its instances, overrides method 2, and adds yet another method, method 3. So we've actually got 3 instance variables in Class B instances. There's 3 instance variables and 3 methods. So how is this actually expressed inside the JVM? Well, so as you might expect, they put these together in a scheme which is called concatenation, which basically means that field X, the one defined by Class A, is always at a fixed offset from the beginning of an object. So whether an instance is of Class B or Class A, field X will always be at the same location. So the JVM always knows where to look for field X. Similarly, for field Y and field Z, those are at fixed offsets. And if somebody were to create a subclass of Class B, then those fields would still be in that location for instances of that subclass. So let's just down at the bottom, the gray rectangle there. Let's take a look at how a couple of different method calls might be represented or might be executed. So here, associated with each class is something called a vtable, which contains pointers to the methods that that class can execute. And so because Class B is a subclass, an extension of Class A, then its vtable actually has pointers to the appropriate method. So just looking through this, so Class A, because Class A and Class B share the same method 1, Class B did not override method 1, both of the first entries and both of their vtables point to the same method. So method 1 is always at entry 0 of the vtable, and you simply follow the reference there and you find the right method. Method 2, however, B did override, redefine, and so the second entry in each vtable always points to method 2, and you can see that there's actually 2 different implementations, Class A.method2 and Class B.method2, and those entries actually point to the appropriate method. And then finally, because Class B has added an additional method, then the third entry in its vtable will actually point to that method. So it's a similar approach to the way that fields are laid out, because vtables are essentially concatenations of superclass vtables, but the JVM consequently always knows where to find a method without having to do string compares. It simply looks in the appropriate slot in the vtable. All right, I'm going to try and speed this up here. So execution, we've talked about this briefly. When a class is first loaded, it is run by the interpreter, which basically does a very similar very common interpretation loop. You get the next bytecode, you execute it, and then go back and get the next one, and so on until the program's done. In addition, modern JVMs also contain a compiler, a JIT compiler, just-in-time compiler, which converts methods into native code, which runs several orders of magnitude faster than interpretation. So this is always a good idea, and compilers continue to get better as time goes on. Again, the compiler has runtime information which it can use to perform optimizations, and so those can be useful. So here's a diagram of how a stack is managed in JVM. So starting from the bottom, the stack is growing upward. So we have a frame, we have a method which has been executing, and it's pushed a number of its parameters on its operand stack. And then it decides that it's going to, or the code calls for it to actually invoke another method. And so the first thing it will do is it'll start pushing the parameters for that method in order, left to right, onto the stack. So parameter 0, which is commonly the pointer to this, or the object when it's an instance method, that's the object that's about to be operated on. Then the remaining parameters, and then it will actually allocate once the method has been resolved, where we're going to call, it'll allocate the local space for all the locals that are needed by that method, and then it'll go ahead and make a native subroutine call, and then go from there. And so the beauty of this is that the information that's passed from one method to the other doesn't have to be copied. So it's pushed on the operand stack of the previous method. You don't have to copy it to another stack or to another place. It's actually referenceable then by the called method. So you can actually, you can actually use the native stack for keeping track of Java execution stacks. All right, we're going to take a look into garbage collection, and again, I think I'm short on time, so I'm going to make this brief. Memory management in Java has a couple of responsibilities. We've talked about them a couple of times already. Allocate memory for new objects, reclaim free memory, and a third thing is you have to mitigate fragmentation. So as objects are allocated and freed, the heap becomes fragmented, and you want to make sure that, or you want to be able to get that unused space even if it's fragmented, and so you may have to do a compaction sort of thing to do that. The secondary responsibilities in Java specifically are to run finalizers, little bits of executable code that get run when an object is reclaimed, and then finally process references, which are sort of soft pointers within the Java language. There are two major garbage collection algorithms that have been used for decades and are still in use today. The first is mark sweep, a mark sweep algorithm where we actually go through the heap and we mark all of the objects that are live, that is, they are currently reachable by some part of the program, the running program. And having done that, having gone through the heap, marked everything that's reachable and therefore valuable, we can then reclaim everything else. So objects that are no longer reachable, that have been abandoned, we can pull those together and put them into some kind of memory pool or free list or something like that. Mark copy is a little bit is similar in one respect, but different, in that the first operation is the same. We go through and we mark the objects that are live on the heap, and then instead of gathering up free space, we actually copy all of those live objects to a new space, and when we copy them, we can then copy them back to back. So they get all scrunched down into sequential memory space, and so that leaves us a whole bunch of unfragmented free space after all of those objects get copied. There are hybrids and variants of both of these. Generational, where new objects are allocated in one region and then ultimately over time get promoted to another region. There are regional collectors like G1 that actually breaks up the heap into decent sized chunks and actually moves objects from one to another. A parallel garbage collector is one that actually uses multiple threads to do its work. And then finally, a concurrent collector is one that actually runs while the application is still running. And that turns out to be an important issue because as heaps get larger, if you don't have some kind of concurrency built into your garbage collector, you may be waiting for a long time for your garbage collector to finish its GC cycle. So there's issues with each of those approaches and each of those hybrids, and we'll just talk about it briefly here. So the first issue with mark and sweep, of course, is that the objects don't get moved. They stay in place, and so that means that the heap eventually gets fragmented as objects are allocated and freed and allocated and freed. You end up with holes, with areas of free space which are small and, and eventually become too small to do an allocation of any reasonable size. So that means that a mark sweep collector has to have, deliberately have a compaction phase eventually when the heap gets too fragmented. Mark copy collectors don't have that drawback, but because you're copying objects from one space to the next, it potentially requires 2 times as much space, right? Because you have to have the space where the objects live and the space where they're going to. And so, so that has historically been a drawback to mark and copy. Generational collectors have a problem in that as objects get moved from one generation to another or from one region to another, you need to keep track of references from one region to the other or one generation to the other, so that as you're collecting one region, you know that if there's a reference to a different region, you don't have to follow that, you don't have to mark that. Additionally, if you're collecting a region that has references into it, you want to make sure that those references are treated as live references, and so those objects get marked and preserved. Parallel collectors, of course, have to deal with atomic operations like any other parallel or concurrent program. Concurrent collectors have to deal with the problem that the Java program is actually modifying the heap as the collector is working. So it can't count on the work that it's done previously as being still in place and unchanged. So all of these collectors at some point or another have stop the world pauses of various durations. Stop the world means the application has to be stopped so the garbage collector can do some of its work. So let's see. I think since I've gone through my half hour, I'm actually just going to call it quits here. I have a demonstration of the concurrent parallel garbage collector that's used in the JVM that Azul Systems sells, which is called Zing. And there's kind of a diagram of how that works, but I think I'm out of time. If anybody's interested, you can contact me, and I can point you to other resources for how this works. So so for the moment, so what that particular garbage collector, which we call C4, actually has some positive attributes in that I'll just show you here. So on the left is a typical a graph of typical pauses. That is, those are places where the Java program is not executing at all, and you can see that there's one pause there that goes over 500 milliseconds and a whole bunch of them over 100 milliseconds. Depending on your application, those can be very disruptive. The same program run on the Zing JVM has much smaller pauses. Worst case was 16.5 milliseconds-ish. And so that's the kind of things that you can get from Zing. So to wrap all this up, the JVM specification describes a model for how the Java Virtual Machine is supposed to work. It is up to the JVM implementer to figure out how to meet that model and do it in an efficient manner. And so over the years, JVM engineers have developed a whole bunch of different optimizations to make the JVM run performantly, and we've taken a look at just a few of them here in this presentation. JVMs are adaptive. They can actually optimize performance based on what's actually happening to the application at a given moment in time. And then there were 3 major subsystems. And then finally, if you're interested, Zing is available for free trial from Azul's website. So that was just a brief tour through JVM and how it works, and I hope that was informative. I think we go into a Q&A session now, so if you have questions, I'm happy to entertain them.